There are two theorems here related to recursion, one for existence and one for uniqueness. To repeat the summary from the previous video, it all comes down to starting with the information of a starting point and a recursion rule, and whether there exists a function that has that starting point and that recursion rule, and whether it is unique. So let's work through stating this carefully. So let me get out of this specific setting with this specific sequence, and let's try to come up with a general way of describing things. So first of all, if you're looking at f from n to n, functions of this type, then you're looking at sequences of natural numbers. If you want to look at sequences of, and then any kind of thing, then you would want to allow any set, capital X, to be here. So now, it's the sort of thing where f of 0 takes a certain value, which will be some element of x, f of 1 will be some element of x, and so on. And x could really be anything. So it could be a collection of real numbers, or it could be a collection of natural numbers, or even not numbers. It could be a collection of functions. Maybe you're looking at a sequence of other functions. Or maybe x could be just a collection of random sets. Just you're interested in a sequence of sets. Who knows? So x could be anything. And then what is what represents this kind of information? The knowing where to start, and then knowing how to step from one to the other. So the start is just going to be some possible output. So something in the codomain. Here it was a natural number, like 2, but in general it'll just be some element of x. So let me call that S for starting point. It's what we'd like f of 0 to be. And then how do I describe a rule for going from one output to the next output? A rule for going from one output to the next output. Like in this case, it was next. That was the rule, right? Take the previous output and then next it. And that's how you get the next output. How do I describe that in general? How about a function from the space of possible outputs, the set of possible outputs, to itself, so that it turns one output into another output. So if that's confusing, I think it will make more sense when I write down what it means for S to be a starting point for f and R to be the recursion rule that describes f. So to say S is a starting point, that's easy. That's just saying f of 0 equals S. So that says f starts at S. And then to say R is the recursion rule is to say that if you want to know f of the next of something, then that's something you can determine by taking f of the thing and then applying R to that. So R is what you apply to the nth output to get the next nth output. You see how that's a recursion rule? And do you see how it must have this sort of type signature, that it must be x to x? That's because it needs to map something of whatever type f of n is, which is going to be an element of x, to whatever type f of next n is, which is also going to be an element of x. So R should map elements of x to elements of x. And to be perfectly clear, to say that f satisfies the recursion rule is kind of a for all n statement. So for all natural numbers, for all elements of the domain of f, we have this. Guess I don't need those parentheses. For all natural numbers, we have that the recursion rule holds. So that means holds at every step. Holds here, here, etc. Okay, so all I'm describing here is basically notation. I haven't said anything. So I'm just writing things down and giving you nice Englishy ways of interpreting them. So when we write f of 0 equals s, think of that as f starts at s. And when we write this, think of this as R is the recursion rule for f. Okay, now we're ready to go state the theorem. All right, so here's a kind of Englishy way of writing both theorems 107 and 108 in the same statement. And we will gradually make this more precise. So given a starting point, S, in some set X, where we want our sequence to take values, and given a recursion rule R from X to X, there is a unique function, a unique sequence in X that has that starting point, the one, the S, and that satisfies that recursion rule. So there are sort of two big statements there. One is existence. There is a function that has that given starting point and has the given recursion rule, and that it's unique. So the existence, that's theorem 107, that's the statement of theorem 107, and theorem 108 states that it's unique. So this is how we've mushed them together by saying there is a unique function. All right, let's see if we can refine this and make it more precise and get rid of the fluff. So the first thing I want to do is take the uniqueness and move that out, since that's going to be a whole other assertion. So let's just make that statement come after. It is unique. So right now it just says there is a function, and then afterwards it says it is unique. So that way I'm going to turn this into theorem 107, I'm going to turn this into theorem 108. Okay, now to make sense of the statement of theorem 107, I should say what it means for f to, quote, have that starting point and, quote, satisfy that recursion rule. So has that starting point. I would say has that starting point means f of 0 is S, and satisfies that recursion rule just means for all n in the domain, if you want to know f at the position after n, immediately after n, well then it's something you can get by taking the f at the position n and then applying r to that. So that's theorem 107. And for theorem 108, it is unique. Do you remember how we formally make uniqueness statements? So we actually discussed it way up here. So this is page 60 of the notes. If you want to say that there exists a green thing, then you might just say there exists x such that x is green. If you want to say there's a unique green thing, that there's a unique green thing, then you would say not only there exists x such that x is green, but also for all y such that y is green, y equals x. So this is how you say there's a unique green thing, is to say if something else thinks it's also green, in fact it was just x all along. So how do we make sense of the statement, it is unique? It is unique means it is unique with respect to these properties. So it is unique with respect to having S as its starting point and having R as its recursion rule. So the uniqueness is this statement that if f and g are two functions that both, so two sequences taking values in x, who both do this, have this starting point and recursion rule, then they are equal. So, and they both start at S, and they both, f has the recursion rule, so let me copy and paste this. So we have this, but then also g has the recursion rule, so we have this but for g. Then f will equal g. That is the statement of theorem 108. So that's what's meant by uniqueness. So these tools will be crucial for defining certain functions whose domain is the set of natural numbers. In other words, it's crucial for defining certain sequences. Now, let me give you a sort of preview look ahead for what we're going to do next time, probably in the next lecture, is we're going to use recursion to iterate the adding one function. So we're going to define a function that has the effect of adding one to things. It basically just carries out next. And then we're going to use recursion to iterate that in order to finally define addition. So the reason this is coming up now is that we want to start doing a little bit of arithmetic, and to define addition you need recursion. You need to define it recursively. Then we can go get into all the fun things that you can do with addition. So on to the proofs of Theorem 107 and 108, or actually lack of proof. I think what I'm going to do is only go through the proof of Theorem 108. Theorem 107 is actually quite an involved proof, and it's really fun and interesting, but the techniques in it, while they are useful and good, they're not actually useful for the rest of this course. So I feel like it would be not the best use of time to sink a lot of time into the proof of Theorem 107. So in your reading, I would say definitely understand the statement of Theorem 107, but go ahead and skip the proof unless you really want to read it. And then for Theorem 108, we'll go through the proof in the lecture, and you can read it if you want to. But definitely understand the statements of these two extremely important theorems. These are just used a lot. And by the way, usually when people use them, if you take any more math classes after this one, you will see people use them. But they will not be so explicit about it. People don't say, now we cite the theorem about the existence of functions that are defined by recursion. Nobody does that. People just do it. People just make the definition and treat it as a legitimate way of defining functions. So people will just say, for one thing, they might actually just write something like this: 2, 4, 6. Let f be the sequence 2, 4, 6, 8, etc. And then they are implicitly using that theorem that tells us that this is a legitimate way to actually define a function. This is really bad though. Hopefully you're not going to see too much of this with the ... What you might actually see is just people will say, let f be the function whose value at 0 is 2 and whose recursion rule is this. Something like that. So you'll be given a starting point and a recursion rule, and no one will make any big fuss about using a theorem there. They will just treat it as a legitimate way of defining a function. Okay, so let's now consider ourselves to have Theorem 107 in hand. And if you have any doubts about it, you can go back and read the proof later or something. But we now have this. And in the next video, let's prove Theorem 108.